Now we will discuss different matching techniques for the transmission line. So already we observed whenever ZL is equals to Z0, obviously that is a matched line, the maximum power will be transferred from transmission line to the load. Whenever ZL is not equals to Z0, that is the load what we are connecting is not matched with the transmission line, some power will be lost, you will get some reflections, right? So in such conditions we are supposed to go for an external matching devices, an external matching technique which will be useful for matching our load with the main transmission line. Now what are the different techniques we have? So already we observed one matching technique, that is a lambda by 4 transformer. Apart from that one, we have one more important matching technique called as stub matching. Now once again briefly we will discuss about these two, what is a lambda by 4 transformer and what is a stub matching. Now observe clearly. Now let us take a main transmission line. This is a main transmission line that what we have with characteristic impedance Z0, and the properties of this main transmission line were unaltered and it's not possible to change. And here we have one load, let us take this ZL as the load, and unfortunately this is also not changeable. Z0 is not equals to ZL. Obviously what you will get is some reflection. I don't want any reflection in the main line. If we are getting reflections in the main line, obviously the transmission system that what we have is an inefficient system. For that what I do is, I'll try to connect a lambda by 4 transformer in between our main transmission line and load. This lambda by 4 transformer with new characteristic impedance Z0 dash will be acting as a matching device between our load and Z0. So here clearly what you can say is, up to this part, this is the load. Here not only this one, along with the lambda by 4 part, this will be taken as the load. Now this is matching with the Z0, that what I am assuming. For that one, what you have to do, you have to take the input impedance at this particular location, and this input impedance is equals to Z0. If this input impedance is equals to Z0, obviously what you can say is, this entire system or this entire load was matched with the main transmission line, and in the main transmission line there will be no reflections. For that what you have to do, what are the parameters you are supposed to consider? Consider the input impedance of our lambda by 4 line. Z in for lambda by 4 line is equals to Z0 dash square divided by ZL. As per our theory, it is required to make this one to equal to Z0, right? So if the input impedance of our lambda by 4 transmission line, that is Z0 square divided by ZL is equals to Z0, then you can say that this entire thing was matched with our main transmission line. Now what is Z0 square? So our Z0 dash is equals to square root of Z0 into ZL. This is the required characteristic impedance of our lambda by 4 transformer or lambda by 4 inverter. So whenever you are supposed to design a lambda by 4 transformer or transmission line, for the purpose of matching, what you have to do is, you have to take this characteristic impedance and use this particular characteristic impedance lambda by 4 line for the purpose of matching between the load and our main transmission line. This is a very simple technique, but the availability of this Z0 dash is a little bit difficult, because you may have different loads and it is a fixed one. Once it was calculated for a particular load, it will be useful for that particular load only, not for the other loads. So if you are using any other load, then obviously you need to change this lambda by 4 transformer again and again. This is a little bit difficult task. For that we have to go for another matching technique, that is called as stub matching. Now what is stub matching? Clearly remember, a simple word stub indicates a small piece of transmission line, nothing more than that. What we are doing is, here in our previous technique we used a lambda by 4 line, exactly the length is lambda by 4, in between our main transmission line and the load, and all they are in series, right? Here what I do is, just I will take a small piece of transmission line, I will connect that transmission line in parallel with the main line at a pre-calculated location for matching application. Here also what I have to do is, just I have to sacrifice a small part of the transmission line. Just you go through the analysis. So where we will connect the stub and what are different parameters which are involved in our stub matching. Let us take, this is a main transmission line that what we have with characteristic impedance Z0, and here I am going to connect a load ZL which is not equals to Z0 Therefore, obviously you will have some reflections, right? My main motto is to match this ZL with Z0. It is not possible to make them equal. But what I have to do is I have to match the load part with the main transmission line so that we can avoid the reflections. And what I have to do is just I have to sacrifice a small part of the main transmission line. Just at the end, I will sacrifice a small part of the main transmission line. If I am sacrificing it, then I may have input impedance at this particular location, right? So Zin will be there. If this Zn is equals to Z0, then I can say that the new load, this is entire part can be taken as new load, right? This new load is matched with the main transmission line. As this new load is matched with the main transmission line, obviously there will be no reflections. So how to sacrifice this part? How to calculate how much part I have to sacrifice? After sacrificing, what I have to do? Just what I have to do is I have to connect another piece of transmission line with characteristic impedance some Z0 or Z0 dash at this particular location in parallel with the main transmission line. So what I am doing is I am connecting a new transmission line that may be either short circuit or open circuit. Now how that particular new stub or a new transmission line, new piece of transmission line will be useful for matching application? Just you imagine what I am saying. We are at load. While we are moving towards generator, right? This is moving towards generator. Somewhere we have Zn is equals to Z0. That what we are assuming, right? Whenever we have Zn is equals to Z0, that the perfect matching is obtained, so that we can take this one as entire new load, right? But in practical cases, that is not at all possible. That Zn is equals to Z0 means here I am writing Zin is equals to Z0, which corresponds to Zin by Z0 is equals to 1. That implies the normalized input impedance is equals to 1 at this particular location, right? So let us take this location is AB location. This is point A and this is B. At AB location, I require Zn is equals to 1. This is my requirement. I am not saying definitely we will obtain that one. This is my requirement that Zn is equals to 1 at this particular location. But whenever we are moving from load to generator, exactly obtaining 1 is not at all possible, because always what you will get is a complex input impedance. So the complex input impedance will be in the form of 1 plus or minus ZB at AB. This is the actual value that what you may get, right? But what you require is 1. So you will get this one, you require this one. So what is the main step after that one? You need to eliminate this plus or minus JB. This plus or minus JB, that is nothing but the reactance will be eliminated by adding a stub. That what I do is just I'll add an extra piece of transmission line that may be either open circuited or short circuited, which will provide minus or plus JB at this particular location. Right? Now, just you observe the equations that what I am going to write here. Now, this is stub, but what I will write? Initially, I am considering the open stub, but later I will tell you only short circuit stub will be useful for practical applications. Right? This is the stub that what I have. Now, Zin I am calculating, right? So, Zin is equals to, so what is the input impedance? It is a combination of the input impedance of our main transmission line. So, simply Zin of our main line plus the input impedance of our stub also, Zin of stub, right? And if you are normalizing that one, what you will get here is Zin is equals to Zin because of the main line plus Zin because of the stub. After adding these two, how much you will get? 1. That is our assumption. This 1 can be obtained how? This Zin because of the main line will be in the form of 1 plus or minus JB, and Zin because of the stub will be in the form of minus or plus ZB. So by adding these two, obviously you will get 1. That is the assumption that what we are considering, right? But here clearly observe what are the parameters we are considering. The parameters we are considering are the impedances, right? The coefficient what we are considering is just Z and it is impedance, and these two lines are parallel. Since these two lines are parallel, we are not supposed to connect add the impedances as our wish. instead of adding impedances as our wish, we need to take the parallel connection. So if you are taking the parallel connection, how these equations will be modified? Don't take them as the final equations. For our understanding only I gave these equations. Now at this particular location I am calculating the resultant impedance. Now what is the resultant impedance? That is nothing but the input impedance at that particular location, Z in. So 1 by Z in is equals to, since these two are parallel, 1 by Z because of, or Z in because of main line, plus 1 by input impedance because of the stub. Now observe here, 1 by Z admittance, 1 by Z admittance, 1 by Z admittance. Directly you can take the admittances. So if you normalize the admittances also, what you will get is Y in is equals to Y in of main line plus Y in because of stub. Now this is very easy to solve. Instead of taking the parallel combinations for the stub, if you are taking the admittances, then you will get a very easy calculation while you are solving that one practically. Now once again clearly observe, whenever we have a load, from that load at some location we are adding a stub. By adding this stub, the reactance part will be eliminated and you will get 1. Zn is equals to 1 corresponds to, the same can be taken as Yn is equals to 1. Yn is equals to 1. 1 can be obtained by adding these two. Now, is it possible to get the input impedance of a stub as a pure reactance? Yes, definitely you can get the pure reactance as the input of any transmission line if it is open circuited or short circuited. Right? That's why I said the open circuit end or the short circuit end will be considered for our stub, but in most of the cases only short circuit stub will be taken, because for the open circuit end a spurious radiation will be there. Right? Now here you are supposed to remember 3 important points. Where you are supposed to connect the stub. Here it's a location where you will get 1 plus or minus JB form. You are going to connect the stub. What is the required input admittance of the stub? Minus R plus JB admittance. Don't take that one as impedance. Required input admittance of the stub is minus R plus JB. To achieve that one, you are using either short circuit stub or open circuit stub with the required length. Now you have to solve this problem using our Smith chart, and that will be very easy to solve. You are at load. You are moving towards generator. Somewhere you will get 1 plus or minus JB admittance. Now eliminate that plus or minus JB. For that connect a stub. Required input admittance of the stub minus R plus JB, that is already known to us. So minus R, from minus R plus JB to the short circuit point, go to that one and calculate the length of the stub. Like this you can calculate the parameters like location of the stub, required input admittance of the stub, and the length of the stub if it is short circuited or open circuited. So with the help of this one, easily you can go for the matching application. But once again here also, depend upon ZL only the input admittance will be divided. Right? So if the load is varied, then what we have to do? For that we have to go for a generalized one, that is multiple stubs. Multiple stubs means not only at this location, you have to go for calculation of another location, connect a stub with different length. Go for another location, connect the stub with different length. Like that, multiple stubs will be there. All those stubs will be generalized so that any load we can connect, and that particular structure will be useful for matching application in our transmission line structures. So these two are the 2 important matching techniques that what we have for matching any load to our main transmission line.